In the vast, infinite expanse of the cosmos, there exist objects so powerful and so mysterious that they stretch the very limits of human imagination. These objects are black holes, cosmic monsters that devour everything, even light itself. Yet, the first conception of black holes did not come from a telescope. It emerged from the realm of philosophy, a daring leap of imagination by a British thinker named Jean Michel in the 18th century. In 1783, Michel proposed the idea of dark stars, objects so massive that their gravitational pull could trap light itself. At that time, telescopes were rudimentary. Observational astronomy could not reveal such objects. But Michel's reasoning was elegant and precise. He built upon the discoveries of Isaac Newton, who formulated the law of universal gravitation, and Ole Romer, who had measured the speed of light. Michel asked a simple yet profound question. What if an object's escape velocity, the speed needed to break free from gravity, exceeded the speed of light? He calculated that a projectile traveling at 7.9 kilometers per second would orbit the Earth. At 11.2 kilometers per second, it would escape Earth's gravity. At 16.7 kilometers per second, it could escape the Sun, journeying into the depths of interstellar space. By extension, if the escape velocity surpassed the speed of light, not even photons could escape. Such an object, Michel theorized, would be invisible. A dark star. To the 18th century scientific community, this was radical. More philosophical speculation than accepted reality. Many considered it a mathematical curiosity, a thought experiment, rather than a real celestial object. Yet Michel had planted the seed for one of the most profound discoveries in physics. His vision challenged humanity to consider objects whose existence could only be inferred by their influence on surrounding matter. The idea of a star invisible to the eye, but capable of bending light and consuming everything nearby, was revolutionary. It would take more than a century to develop the theoretical framework and observational tools needed to truly comprehend these cosmic enigmas. Over a century later, Albert Einstein would transform our understanding of gravity. With his general theory of relativity, in 1915, Einstein described gravity not as a force, but as the curvature of spacetime itself. Created by mass and energy, he realized that a sufficiently massive object could warp spacetime so intensely that nothing, not even light, could escape. Yet Einstein himself doubted such extreme objects could exist. The mathematics allowed it, but reality, he believed, would not. It was Karl Schwarzschild, a German physicist serving on the Eastern Front during World War I, who first provided an exact solution to Einstein's equations. While resting in a war trench, Schwarzschild calculated that a point of infinite density could form under gravitational collapse, creating what we now call a black hole. He defined the critical radius beyond which escape was impossible, a concept we now know as the Schwarzschild radius. To illustrate, Schwarzschild noted that if Earth's mass were compressed into a sphere just 250 times smaller than the Sun, it would collapse into a black hole. Tragically, he died shortly afterward, leaving only this brief but profound legacy. His work showed that black holes were not mere speculation. They were a natural consequence of spacetime curvature. The universe contains regions where known laws of physics reach their ultimate limit. For centuries, black holes remained theoretical. Direct observation was impossible. No telescope could penetrate the veil of the event horizon. In 1978, French astrophysicist Jean-Pierre Luminet used early computers to simulate the appearance of a black hole. His images depicted a dark, swirling abyss, surrounded by a luminous ring of matter, the accretion disk. This disk, composed of hot, infalling gas and dust, emitted energy across the electromagnetic spectrum, allowing indirect observation of the otherwise invisible black hole. Yet, until 2019, all images were simulations, guided by theory rather than direct observation. On April 10, 2019, everything changed. The Event Horizon Telescope, a global network of radio observatories, captured the first-ever image of a black hole. Located in the center of galaxy M87, 55 million light-years from Earth. The data required over 2 years to synthesize, but the result confirmed theoretical predictions. A dark core, surrounded by a luminous ring of infalling matter. This achievement was historic. It confirmed Einstein's general relativity, validated Schwarzschild's calculations, and vindicated Jean-Michel's vision from more than 2 centuries earlier. For the first time, humanity had seen the unseeable. Observations reveal that nearly every galaxy hosts a supermassive black hole at its center. Though these black holes occupy less than 0.1% of the galaxy's volume, their gravitational influence dominates the motion of stars and gas. Our own Milky Way harbors Sagittarius A star, a black hole with a mass of roughly 4 million suns. Stars near this black hole orbit at incredible speeds, up to 24,000 kilometers per second, nearly 8% of the speed of light. The gravitational dance of these stars defines a galactic habitable zone, regions where conditions for life are stable. The solar system's location, roughly midway along the Orion Arm, places us in an ideal position, safely distant from the destructive forces of the galactic center. If Earth were closer to Sagittarius A asterisk, tidal forces would be catastrophic. Planets could be torn apart. Life as we know it would be impossible. Our position in the galaxy is not random. It is a quiet haven within a vast, dynamic system. The Milky Way's habitable zone is a ring-shaped region, spanning tens of thousands of light-years, where stellar radiation, gravitational stability, and metallicity align to favor life. Within this cosmic safe zone, Earth formed, and life emerged. A delicate balance orchestrated by the invisible hand of gravity. What lies inside a black hole? To answer this, we turn to the concept of the singularity. British physicist Stephen Hawking and mathematician Roger Penrose formulated the singularity theorem. Any object collapsing beyond a critical limit will inevitably form a singularity. At the singularity, density becomes infinite. Volume shrinks to 0. Classical physics ceases to apply. Space and time themselves break down. There is no before or after. Only a state of infinite curvature. This extreme state mirrors the conditions of the universe at the moment of the Big Bang. The singularity represents a boundary of knowledge, a region where our current understanding of physics cannot reach. It is a place where gravity dominates completely, where time and space are twisted beyond recognition. Understanding singularities challenges the foundations of science, forcing us to confront the limitations of human comprehension. Not all singularities are hidden behind event horizons. Some, theoretically, may be naked singularities, exposed to the universe without a shroud of darkness. These singularities, if they exist, could reveal the extreme warping of spacetime to outside observers. Near a naked singularity, matter could be accelerated beyond light speed, potentially leaping into alternate regions of spacetime. While purely theoretical, these objects hint at natural wormholes, cosmic shortcuts connecting distant regions of space. They challenge our understanding of causality, energy, and motion, pushing the boundaries of imagination. Naked singularities remain hypothetical, but they inspire physicists to ask bold questions. What lies beyond the event horizon? Could nature permit travel through these extreme regions? Wormholes, first proposed in 1916 by Ludwig Flamm, and later formalized by Einstein and Nathan Rosen, are theoretical tunnels connecting separate points in spacetime. Unlike black holes, which are physical objects, wormholes are structures of spacetime itself. If traversable, they could enable instantaneous travel across galaxies, or even between universes. Gravitational wave observations, such as black hole mergers detected in 2016, have hinted at subtle echoes. phenomena that some speculate could indicate wormhole-like structures. The concept is mind-bending. A tunnel through spacetime, bypassing the vast distances of the cosmos, making the impossible possible. If wormholes exist, they would transform our understanding of space travel, allowing civilizations to circumvent the speed of light barrier entirely. Every black hole, from stellar remnants to supermassive galactic anchors, is a gateway to understanding the cosmos. Theoretical physics suggests that advanced civilizations could harness wormholes for interstellar travel, bypassing the immense distances that constrain human spaceflight. To reach even the nearest star, Proxima Centauri, with current spacecraft speeds, would take over 13,000 years. Wormholes, if real, provide the only plausible mechanism for civilizations to traverse the universe efficiently. They offer a glimpse into a future where distance is no obstacle, where travel across light years could occur almost instantaneously. As French astronomer Jean-Pierre Luminet once remarked, black holes are the ultimate fate of dying stars, the extreme endpoint of gravitational collapse. They are as absurd as they are beautiful. And in studying them, we study the universe itself. The story of black holes is a story of humanity's quest to understand the cosmos. It is a journey from imagination to theory, from theory to observation, and from observation to wonder. From John Michel's dark stars, through Einstein and Schwarzschild's theoretical breakthroughs, to the Event Horizon Telescope's first photograph, black holes have evolved from philosophical speculation to tangible cosmic reality. They challenge our understanding of space, time, and gravity. They hint at possibilities that transcend imagination, wormholes, naked singularities, and perhaps the very origins of the universe itself. In exploring black holes, we explore the edges of knowledge, where physics meets philosophy, where humanity peers into the deepest mysteries of existence. Black holes are more than astronomical objects. They are the keys to the ultimate questions. How does the universe work? What is the nature of reality? And what lies beyond the veil of spacetime? The story of black holes is the story of our quest to understand the cosmos. A quest that has only just begun.